Hi gang, so we're going to factor another higher order polynomial. So remember, this takes a lot of steps and a lot of skill set to do this. So we're going to start with Descartes' rule of signs, and again that just gives you an approximation of the number of positive real zeros you have and negative real zeros that you have. Okay, so there's a couple ways to think of zeros. The function can factor with its zeros, or you can think of it as their x-intercepts. All right, we'll talk about it again as we get further down, but what you're trying to do at the initial stage is approximate how many zeros are in the problem. So since it's a fifth degree, that means that it will factor into 5 binomials and that it will have 5 zeros. Okay, so let's get started. It's our second example of this. So if you recall, the number of positive real zeros is the variation in sign of f of x. So you're looking for every time the term changes from positive to negative or negative to positive. All right, so here we go. Let's look at the first term here. X to the fifth is positive. So from x to the fifth to x to the third, there's no sign change. There's no variation in sign. From x to the third to 2x squared, there is no change in sign because you're going from a positive to a positive. But now as we go from positive 2x squared to negative 12x, there's a change in sign. That's a variation, so we'll count that as 1. All right, and then as we go from the next one, from negative 12x to 8, that's your second variation in sign. Let me just get my elbow a little better. Okay. All right, so there's a total of 2 variations in sign. Now remember that Descartes' rule of signs cannot account for complex conjugates. It doesn't know when you have a complex pair as a 0. So since it's a pair, it means it counts for 2. So that means that this problem could have 2 positive real zeros or none. Okay? So it's 2 positive real zeros or none. Remember, you have to keep subtracting 2 until you get to 0 or 1. And that's, so you have to take out the complex pairs within the estimated real zeros. Okay, now let's do the number of negative real zeros. So in order to do the negative real zeros, you have to find the variation in sign of f of negative x. So the first thing you have to do is actually create f of negative x, which means that everywhere you see an x, you have to replace it with negative x. Okay, so I took our original polynomial, and everywhere you see an x, I replaced it with negative x. Now you're going to simplify that. If the exponent is odd, the negative will live, right? It will remain because you have an odd number of negatives. But if your exponent is positive, the negative will go away, right? So if you have an odd amount, the negative stays, an odd exponent, I should say. And if you, oh, that's another odd one. All right, so now even, right? Because you have 2 negatives make a positive. So anytime you have an even exponent, the sign stays the same. Anytime you have an odd exponent, the sign changes. Okay, so here we go. We've created f of negative x. And now we're going to look for the variation in signs to find the negative real zeros. So let's take a look here. So we go from a negative to a negative, so there's no change in sign, no variation. Now I go from here to here. That's 1 change in sign. So I'm going from negative to a positive. All right, now let me go from here to here. That's a positive to a positive, so that's no change in sign. and I go from here to here, that's a positive to a positive, no change in sign. So there's a total of 1. There's no point of me subtracting 2 from that to see if it has complex conjugates, because it would go negative, right? You can't have a number, you can't have a quantity that's negative. Like you wouldn't buy like negative amount of pens, right? You have to have it, the quantity has to be positive. So I can't subtract 2 because it would become negative. It would become -1. All right, so how you have to think about this, and I know this section is difficult, but how you have to think about it is that this polynomial has either 2 positive real zeros or none. Descartes' rule of sign doesn't tell you which case it is. For the negative real zeros, we know for sure we have 1. So when you get an answer like that, it doesn't mean that it might have 1. It means that it has 1. Okay? Now, I'll make you a little chart, and it's not that you have to make me the little chart on the exam, but I just want to talk you through a little more information what you're looking at. So because this is a 5th degree polynomial, it means that in terms of zeros, it has a total of 5. Okay, this chart is ending up a little bigger than my brain wanted it, but that's okay. All right, so number of positive real zeros. I just make you a little chart. You don't have to make this for me if you don't want to. If you want to, it's very nice. Number of negative real zeros. And complex conjugates. Let me write complex numbers. I won't say pairs because I want you to think of them individually. Complex numbers. Okay, so for case 1, we know this has 5 answers. So what's one way that the 5 answers could happen? So for instance, I know that I could have 2 or I could have 0 positive real zeros. Now, in the case that I have 2 real zeros, how many negatives will I have? Well, we already discussed that you only ever have 1. So I would only have 1. Okay? Now, in this scenario, then how many complex numbers would you have? And why are you coming up with that answer? So your logic should be, if I'm looking for 5 zeros, and I know that I currently have 3, then 2 of them must be complex numbers, because it has to add to 5. Now for case number 2, where you may have no, because it's not telling you exactly which one works. So if you have no positive real zeros, and you only always have 1, right? If there's no options, it's just whatever gives you. You only have 1 negative real zero. Then how many complex numbers must be in the answer for you to reach your 5th degree polynomial? Right? It has to be 4. There's 4 complex numbers, or you can think of it as 2 complex conjugates or 2 complex pairs. All right, so that's going to be the breakdown, and I'll come back to that at the end because I know that looks very abstract, but just see if you can sort of follow, like, how did I find the number of positive real zeros, right? That was the variation in sign of f of x minus the complex pairs. And then how did I find the negative real zeros? Well, that was f of negative f. Sorry, that was the variation in sign of f of negative x. And then you had to count the variations in sign, okay? That's how you find that. That's the process. And we can come back and look at that again. I don't want to make this video super, super long, or I'll cut it in half. Now, in class, I usually give the example of the football teams. Not that I know football at all, I don't. So you have to bear with me if I totally destroy the game. So, you know, in a football game or any game, you start with a whole bunch of teams. And at the very end, you get the winner. It's the same thing with the rational zero test. You're generating the teams, so to speak, and when you do the work, you find the winners. So that's what I'm going to do. I'm going to right now generate the teams, and that's what this rational zero test does. So how you do the rational zero test is it's the constant over the leading coefficient. So you take the constant, which is 8, and you put it over the leading coefficient. All right, the leading coefficient here is a 1, right? If there's nothing here, the default is a 1. Now, what you want to do is you want to write down all the factors of each side. So for instance, all the factors of 8 would be 1, 2, 4, and 8. And 1 is just 1. Now, I didn't give you a terribly hard example. If there's a lot of factors in the numerator and denominator, this can get crazy, but it's not right now, okay? So this is not too bad. So you basically have 1 over 1, 2 over 1, 4 over 1, and 8 over 2. Sorry, 8 over 1. 1 over 1, 2 over 1, 4 over 1, 8 over 1. If there had been another number here, like for instance a 2, my brain was, that's where it was going. Like let's say you had another number here, you would have to put them all over that second number as well. So the amount of quote unquote teams can be enormously large for some of these problems. It can get very large quickly. So the possible winners that I have right now are 1, 2, 4, and 8. Now, when you create this list, it's your job to find the factors, and then it's also your job in this section to take the positive and negative of each of the factors. So I'm going to take the positive and negative 1, positive and negative 2, positive and negative 4, and positive and negative 8. So what I'm saying is that the zeros of this problem, otherwise known as the x-intercepts, could potentially be, and I'm going to put this in numerical order for you, negative 8, negative 4, negative 2, negative 1, 1, 2, 4, or 8. So what this factors into is going to have these numbers, we don't know which ones yet, are going to be mixed in there, okay? Our job is to figure out which are the ones that we will use to factor this polynomial or to factor this polynomial or to find its x-intercepts, okay? That's the tricky part. So again, the rational zero test will generate the potential zeros that work in the original polynomial. Okay, again, it's not giving you the exact answer, but the exact answer is within the pile. It's just up to you to dig it out. All right, so how do you dig it out? You're going to do synthetic division. Now, we talked a little bit about upper and lower bounds, so let me just review that really quick. So if you test a zero, in your synthetic division, a positive zero, like let's say you try like a 2 or something, a positive number, and what comes out is some kind of variation of positive, negative, that is considered an upper bound, meaning that nothing higher works. An upper bound means nothing higher works. So if I find that 2 is an upper bound, I would not then go test 8, because if nothing is higher than 2, then 8 would not work. Okay, so the only tricky thing about an upper bound is it's not necessarily the lowest upper bound. It's not necessarily the lowest upper bound, okay? So that's a little, we have to be careful with that. All right, now the other one, I hope the lighting is still good. Let me fix this a little bit. All right, now the other one is if you put a negative number in here, like negative 2. And what happens, oh nuts, my brain did this backwards. Okay. My brain did this backwards, I'm sorry. This is all positive, my brain did a negative. I'm a little tired, I'm a little shot today, I'm so sorry. Okay, let me say that one more time. If you put in a positive number and you get all positives out, that's considered an upper bound, okay? My bad. It's a lower bound if it alternates. So we get positive, negative, positive, negative. So if you put in a negative number and you get an alternation of signs, then that means that nothing lower works. Nothing lower works. So for instance, if I have like a negative, I would not then go test a negative 8 if negative 2 is a lower bound, because nothing lower would work. Now again, I know I'm giving you a lot of information, but when I say lower bound, this doesn't necessitate that. This doesn't necessarily mean that negative 2 is the highest lower bound, right? Negative 1 might have been the lower bound. So it's not necessarily giving you the highest lower bound. I know it's a little hard to understand, but when you think it through, you'll realize what I'm saying. Okay, so I gave you that, and the purpose of those tools were so that If you had a huge amount of numbers you were testing, that would streamline the process and it would take less effort for you to find it. Okay, so this is a really great tool. As well as Descartes' rule of signs, it's a really great tool. All right, so now let's go ahead and try to figure out what the winning zeros are. Now this is where all the work happens, because you don't know who the winner is. You don't know who the winners are, so you have to sort of grunge through the pile and figure it out. All right, so let me write down my polynomial. So it's a 1. You don't have a 4th degree, so don't forget you have to represent each term. I don't have a 4th degree, so I have to put a 0 there. Okay, so there's my coefficient of my 5th degree, coefficient of my 4th degree, which isn't there, coefficient of my 3rd, coefficient of my squared, coefficient of my linear, coefficient of my constant. All right, now I'm going to make a suggestion here, and it doesn't have to be you, okay? It does not have to be you. You decide what works best for you. I will just make suggestions, but you want to develop your own sense of critical thinking and what you think is the correct process, and I will just advise, give you suggestions. So these are some things you can think about when you're taking the test. You're not sure whether it has 2 positives or no positives. If it has no positives, if this problem happens to have no positives, you could go through every single positive in your list and